A very good afternoon to you and welcome to the latest in our talks for the wonderful Big Bang Week at Wigtown. A special shout out before I start to our sponsors who are listed just below me on the screen. My name is Leo Enright. In my day job, I'm a space commentator. In normal times, I spend my time traveling the world, reporting on space missions from Cape Canaveral and elsewhere. But right now, I would much prefer to be in Wigtown, as I'm sure many of you would prefer to be in that wonderful town for this great event. Hopefully next year we will all get together again in Wigtown. But in the meantime, we have a very special treat for you this afternoon. Before I introduce our latest guest speaker, I'd like to just remind you that you can ask questions at any point during his talk. If you simply go put your question in to the comments section on YouTube or Facebook, and at the end of the presentation, I'll be very happy to ask them. I should also say that as a special treat, we are giving a free voucher, a book voucher, to the best question from a young person. Now, how you define yourself as a young person is up to you, but when you're putting in your question, if you want to be considered for the special book voucher prize for the best young person's question, put your age in brackets after your name. But as I said, put your questions in the comments section of YouTube or Facebook. So now let's move on to the big event this afternoon. I want to introduce you to Dr. Joe Zuntz of the University of Edinburgh. He is teaching a course in discovering astronomy. And Joe, perhaps you might tell us a little bit about the course and about the wonderful astronomy course that you teach at Edinburgh before we start.
Oh, thank you, Leo. Yes, very nice to be here. Thank you very much, and to all the organisers. Yeah, so I'm lucky enough to teach our wonderful undergraduates a course on discovering astronomy, trying to give them the great breadth of astronomy, going from tiny things like stars and planets up to average-sized things like galaxies, which for me as a cosmologist is my frame of reference.
And so, yeah. One question that I get asked a lot by mums and dads when they're young people are considering college, after they've worked really hard at school and they're thinking about going into college, and a young girl or a young boy comes to mom and dad and says, I'm thinking of doing astronomy. And a lot of mums and dads ask me, why should my child do astronomy? Where are they going to get a job with that? Can you answer that question again before we start?
Absolutely. So we're very lucky in astronomy that what we do is, although we apply it to things like the stars and the galaxies and the planets and the moons, the techniques we use and the ideas that we use are an absolute perfect fit for the modern economy. So one of the biggest jobs that is growing in the current world is data science. So that's how you analyze data, how you present it, how you understand it. And that's exactly what astronomers are perfectly trained to do from a very young age. So it's no longer the idea that the only thing you could do was go up to the top of a mountain and look upwards. You can now get a very sensible job as well.
Wonderful, Joe, wonderful. Okay, so let's move on to the big event. Can I introduce again Dr. Joe Zuntz?
Thank you very much. Thanks very much again. Wonderful. So thank you for having me. Very nice to be here. And I think my slides should appear if I say some magic words like next slide, please. There we are. Fantastic. So you can see me in the corner and you can see my slides appearing there as well. Wonderful. So thank you. Yes. So I'm talking about the dark sector, which is at the core of modern cosmology. So cosmology is what I do. I'm a cosmologist and we study the universe on its largest scales. We're interested not in planets or stars, but on galaxies and on how the universe as a whole is behaving. And what I'm going to try and persuade you of in this talk is that most of what's out there in our universe is completely unknown and very, very hard for us to understand. It's what we call dark, and that's what the dark sector is. Now, I'll begin our story, if you go to the next slide, 100 years ago, when this man went to this island and took this photograph. So this happened in May 1919. This gentleman took this photograph on this island, from this island. So you go to our next slide. Let's start with the man. So the man is Arthur Eddington. He was born in 1882 and was an astronomer working at this time at Cambridge. He grew up to Quaker school teacher parents, came from a very modest, very normal background, but he did well enough at the University of Manchester that he did a very successful career in astronomy. And by this point in 1919, he was already a very powerful, or very influential astronomer. Absolutely amazing Renaissance man overall. He gave his name to a metric for how for long distance cycling, as well as being an astronomer. He was an avid long distance cycler. He gave his name to a metric for how far you can cycle in a day or in many days. He was a very literate man, very interesting bookish man. He celebrated the work I'll talk about in a moment by writing a parody of the Rubaiyat of Omar Khayyam. So that gives you an idea of the breadth he was. Very witty man as well, and apparently very warm as well. He was known for having these very fierce scientific disagreements, but being really good friends with the people that he was disagreeing with. So very interesting man overall. If you go to the next slide, let's look at our island. So the island is Principe. So today, the island of Principe is one of the two islands that makes up the nation of Sao Tome and Principe. So you can just about see them there. They're two very small islands off the coast of West Africa. You're looking at the whole of the island, essentially, in that photograph there. Today, its population is about 8,000, and it's part of this independent nation. Back in 1919, this was a Portuguese colony, as it had been since the 15th century, uninhabited before that, but became a slave colony, unfortunately, for several hundred years. And actually, in 1919, when our photograph was taken, it was only about 40 or 50 years since slavery had been abolished on the island. So it was a place in a time of great change on the island of Principe. But the reason we're interested in it today was what was happening on the island of Principe at this time. And what was happening on May 1919 was a total eclipse of the sun. And if you go to our next slide, let's look at our photo of this that was taken. So a solar eclipse is when the sun is blocked by the moon. So what we're looking at here is the moon in front and then the light from the sun all around the edges. What was interesting about, so these things happen all the time. There was nothing particularly special about this one. It was just a very convenient one for the science of relativity to understand what's going on. So why were we interested in this photograph? Why was Eddington interested in going all the way to this island just to take this photograph of a solar eclipse? Why couldn't he wait just a few years for the next one to be somewhere more easy to access from Europe? Well, to answer that question, we're going to have to go back even further in time. We're going to have to go far back to the year 1784, when an astonishingly prescient man, if you go to our next slide, called John Michell was writing. Now, John Michell is undeservedly obscure. He was a fascinating scientist. He was described as the only interesting scientist in the century after Newton at Cambridge. So everyone else at Cambridge was useless in that 100 years, apart from John Michell. He's so obscure, there isn't even a portrait of him in existence. That's just some other guy I found a photo of, a portrait of instead, just to illustrate the slide. So John Michell was ahead of his time in many ways. He was a very broadly skilled scientist, and both in theory and in experiments. But in 1784, he wrote, talking about light, he wrote, "Let us now suppose the particles of light to be attracted in the same manner as all other bodies with which we are acquainted." So what John Michell was saying here, what he was trying to get across, was the idea that he thought gravity should affect light in the same way it affects everything else. So you and I are pulled down to the ground by gravity. If you were to fire a bow and arrow into the air, your arrow would go in a straight line first, but then gravity would make it bend down and land on the ground. And what John Michell was saying here was that he thought the same thing should happen with light. If I were to shine a laser pointer up into the sky, Michell was saying that gravity should pull down that light as well. Now, not as much, because light goes so fast, much faster than my arrow, But his idea was that the same thing should happen to a very, very small effect. So that was the first suggestion way back in 1784, that gravity should affect light just like it affects ordinary matter, ordinary things. The question wasn't really addressed for a long time. So very ahead of his time, John Mitchell. This was a long way before anyone could actually measure this effect. John Mitchell, far ahead of his time in this and many other things. He also suggested black holes later in this same letter, astonishingly far ahead of his time compared to everyone else. But it was only in 1919 that we were finally able to measure this, to measure and see if John Mitchell was right that gravity should bend light or not. That was the question that Eddington was trying to address. So how does a solar eclipse help us look at whether gravity bends light or not? That was the question. If you go to our next slide, we can have a look. So here's the case without a solar eclipse, where we're sitting there on the Earth on the right-hand side, and there's a star, a very, very distant star, an extremely long way away, like all our stars. And these stars send light out in all different directions. I've drawn a few light rays there coming out from our star, going into different directions. But really, it's sending out light in all different directions. And one of those light rays happens to hit the Earth, and if we're very lucky, hit our telescope. So we can see the star and see which direction the star is in. So that tells us which direction we see the star as being, is the light ray that hits there. But now, let's see what happens when the sun comes near our rays of light. So here we are, the sun, as it gets near the rays of light, we've said that the sun might bend those rays of light. And that is indeed what's happened. Let's move the sun closer and closer and closer, and finally really, really close. So you can see what's happening here is that the gravity from the sun's amazingly strong gravitational pull is bending those light rays. The sun has bent those light rays so much that they curve around and no longer hit where they used to be. The light ray that used to hit the Earth has now gone off in a completely different direction and hit somewhere else, and a totally different light ray is hitting the Earth. Now, in real life, of course, it's the Earth that's moving here, not the sun. But the effect is the same. The effect is the same whether it's the Earth that moves or the sun that's moved. The same thing happens. So now our sun has bent all these light rays. What happens from our perspective? Well, if we're looking out of that light ray, the next slide will show us what that looks like. We will see the light ray coming in from that star, but it's been bent. So if we just look at the star, we see it in a completely different direction. If we assume, as we always would, that the light has come straight towards us and we look out in a straight line, we'll be looking in a different direction to the star, to where the star used to be compared to where it is with the sun bending its light. So we've had this big difference in where the sun looks like and where the star looks like. And our next slide shows how there was that change in the position of the star. And what Eddington was trying to measure by taking this photograph was the difference between our red line and our white line there. So the difference in where the star used to be compared to where the star looks like it is when the sun bends its light by gravity. So John Mitchell predicted this back in 1784, but he was thinking in terms of Isaac Newton's theory of gravity. He was thinking of Newtonian physics, which makes a prediction for how much this bending of light should happen. But the interesting bit was that Einstein predicted this phenomenon as well. So Einstein's brand new theory of general relativity also said that the light should be bent. It said the same thing should happen, but it disagreed with Isaac Newton about how much. If you look at our next slide, the two theories, Isaac Newton's theory of gravity and Einstein's theory of general relativity, predicted different things for how much this light should be bent. And in particular, Einstein said that that angle, I've called it X on this diagram, that angle by which the star seemed to move when the sun was nearby should be twice as much as Isaac Newton thought it was. So that was what Eddington was trying to measure. He was trying to look at the difference. He was trying to say, how much did our stars move? And did the amount those stars move agree with Einstein or Newton, or as often happens when you do experiments, none of the theories whatsoever. So that's why they had to hire a sailing ship. They had to go all the way down to the island of Sao Tome for this total eclipse of the sun. And the reason for that is this effect happens all the time. The sun is always bending the light from stars, but it's usually an extremely bad idea to point your telescope directly at the sun. Because at best you'll have set fire to something, and at worst you've melted your eyeballs because the sun's just too bright. So it's only during a solar eclipse that we can actually see this effect happening. And if you go to our next slide, we can look at the photo that Arthur Eddington took. Now, there's the sun in the middle there, the big obvious thing, and the moon blocking it out. But what Eddington has marked with lines in this photograph, you can see the little lines in the top right-hand corner there. Those lines mark the positions of stars that he could find in this photograph. And you can just about see, depending how good your eyes are, there's a tiny dot in the middle of those lines, which is where the stars are. So those lines are drawn on, but they're marking the positions of the stars. So Eddington managed to make this image and take this photograph to see how much the stars had moved compared to where they used to be. Now, this was an enormously big result. He made this measurement, and the result was that it agreed with Albert Einstein's theory of general relativity. And this was the first great big test of relativity. It was the first thing that proved that relativity could be a real theory of gravity, could actually be describing things. All these amazing things in relativity, curving space-time, gravity distorting the fabric of space, clocks running fast and slow. This idea was all, the first experimental proof we had of this theory came from this one photograph from Arthur Eddington. This was an immediate media sensation. If you go to our next slide, we'll see some of the headlines at the time from the New York Times. The New York Times wrote, "Lights all askew in the heavens, men of science more or less agog." I love this line, "Stars not where they seemed or were calculated to be, but nobody need worry." So absolutely wonderful, wonderful hyperbole and beautiful language from the New York Times headline writers there once Eddington's results became public knowledge and were actually released. So this was a huge thing. It was also very important politically on some level. It was seen as a rapprochement because it was a British scientist confirming results from a German theorist. So in the immediate aftermath of World War I, that was seen as a very positive move that science was starting to bring the world together again. So it was a huge discovery in the media, in politics, and it really kicked off the century of cosmology that we've been doing since. This was the first big push towards finding out how the universe worked on its large scales. So for a long time, this photograph of Eddington's was actually the only case we could find of this effect, which we've now come to call gravitational lensing. So that's cases where gravity from something like our sun acts like a lens by bending light. So you may have glasses like mine. Glasses like these ones bend the light that goes into them, in my case, to make it focus on my back of my eyes properly. But in the case of the sun, it's bending the light and changing the position of things. So like I say, for a long time, this was the only one of these images like this. But finally, in the last 30 years or so, we've been able to find more examples of this gravitational lensing effect that we can see. And if you go to our next slide, let's look at one of them. This is from a telescope called SDSS, the Sloan Digital Sky Survey. And what you're seeing here is another great example of this gravitational lensing. So locally in our solar system, we can look at the sun bending light. When we look out into the universe, we look for different things. We look for galaxies bending the light of other galaxies. So what we're looking at here, and I've labeled it in our next slide, is a really big galaxy in the middle. So that's the big bright one right in the center, and those are galaxies behind it. Sorry, I forget that not everyone sees these beautiful pictures all the time, because it's one of the great perks of the job of being an astronomer. When we look out into the distant universe, what we see is galaxies. Every single dot in this photograph is an entire galaxy. Even the really, really tiny ones you can see right in the background. Even those tiny, tiny dots are entire galaxies with 100 billion stars, each the size of our sun inside them. So you really do forget being a cosmologist or being an astronomer, just the vast scale of these things that we're looking at, 100 billion times the size of our solar system, even in a pixel of that image. So these vast images are truly wonderful to behold. But here we're going to be massively disrespectful to our galaxies. Here we're really just using them as a little backlight. So we're just saying, all these galaxies, we don't care about you. All we want to do is see how the light from them is being bent and distorted. And that's what's happening here. Those strange arcs that you can see that I've labeled there are distortions of background galaxies. So if you've got glasses, if you turn your glasses to funny angles, you'll see that the things, if you look through the glasses, that things get bent and distorted and twisted. If you've not got glasses, you can do this with a wine glass as well. If you hold a wine glass up and look down its stem, you'll see the same kind of effect, that the light gets distorted and twisted around. And sometimes distorted into these curved arcs that we're seeing there. So each of those strange arcs that we're pointing at there is actually a single galaxy, ordinary shape, little blob somewhere that's been stretched and bent out. So we see these strange arcs instead. So that's an example of a gravitational lens. I've got another one on our next slide, which is an even weirder looking one. So again, we've got a really big, heavy galaxy in the foreground. This is a picture from the Hubble Space Telescope. There's a big, heavy red galaxy in the foreground, and there's a blue galaxy behind it that, again, is lined up so perfectly that it's made this weird ring around the galaxy. And that's called an Einstein ring. And that's one galaxy, again, sitting right behind this red one, but somehow arranged, or not somehow, but by pure chance, arranged so perfectly at exactly the right distance that the light from it's been spread out into this weird, strange arc. So again, like looking through a perfect lens at something exactly the right distance away. So these things are extremely weird, and they're very beautiful, I think, but they're also extremely strange things. But they're very useful things as well, because lenses like these ones are the only way we have or one of the few ways we have of weighing things out there in the universe. So, but what do I mean by weighing things? I mean finding their mass. We can use lenses like this one, systems like this one, to tell us what is the mass of the thing in the middle? How heavy is it? And that's because just like the stronger gravity is, the more you're pulled down, the same thing happens here. If I were sitting on the moon and I were to jump, I would jump about 6 times higher than I do on the Earth. On Jupiter, I could barely jump at all because its gravity is so small. So high. So the stronger, the bigger, the heavier something is, the more it pulls stuff towards it. And that works with light as well. The bigger our galaxy in the middle is there, the more this galaxy will be distorted and the bigger this ring will be, because the more the galaxy will bend the light from the background behind it. So pictures like this one let us weigh things out in the universe. It's like having a giant pair of scales that we can use to weigh things on cosmological sizes. And when we do that, something very, very surprising happens. When we make measurements like this, and when we look at the sizes of these rings, and we do our calculations that tell us how big and heavy this galaxy is, something very weird happens. If you go to our next slide, I'll look at the kind of 2 sides of this. There's 2 ways that we can work out the mass of that galaxy in the middle. There's 2 ways we can weigh that galaxy in the middle. The first is just by looking at it. If you look at something and you know what it's made of, you can tell roughly how heavy it is in many cases. And that's the case here. We know galaxies are made of stars, and we know how bright stars are, and we can see how bright the galaxy is. So we can say, this galaxy looks like it's got 200 billion stars in it, based on its brightness. We can say it's got the same brightness as 200 billion stars, so it's probably got the same mass as 200 billion stars as well. That's a kind of reasonable assumption. So by looking at these galaxies, we can work out the mass of them by looking at how bright they appear to us. That's method number 1 for weighing a galaxy. Method number 2 is on our next slide, and that's by measuring the gravitational lensing. We can measure the size of this ring. The bigger this ring is, the more the mass in the middle is bending gravity. And so the bigger the thing in the center must be. So we can tell how big the thing in the middle must be from its gravity. So now we've got two methods for weighing a galaxy. Method number one, how bright is it? Method number two, how much does it bend the light from behind it? And you'd think when you have two ways of measuring something, then you would they should agree. They should tell you the same thing. If you've got two good ways of measuring the same thing, then hopefully they should give you the same answer if you measure them together on the same thing. And unfortunately, or perhaps fortunately for my employment prospects, that doesn't happen. There's a very, very big difference between what we get when we measure these two things about a galaxy. So if you go to our next slide, I've kind of summarized this. We can measure the stars and the mass of the visible stuff, and we can measure the gravity and the mass of everything that's there. And what we find, not just in this galaxy, but in every galaxy that we can look at, every system we can look at, whether it's one galaxy or many galaxies, whether it's a simple system or something complicated where galaxies are crashing into each other or colliding, any place we look out in the universe, we always find that the total mass, the mass that we can see from gravity, is always about 5 times bigger than the mass from the stars and the gas that we can actually see. So this was immensely confusing from as soon as it was discovered. The question is this idea: how can there be all this stuff that we just can't see out there in the universe? How could this be? What could be? It can't just be black stuff, because then it would block the light of other things behind it. We know it must be something. It can't just be material like that. So the question is immediately, what is all this stuff, like sort of 80 or 90% of the universe? What is all this stuff that we can't see? What's going on was the immediate question that measurements like this raise. What's out there in the universe that's making up all this invisible matter out there everywhere? So now, if this was the only way we had of measuring this effect, this mass, people would be very, very suspicious. I've made an extraordinary claim here that there's all this invisible mass out there. And there's an old saying, I think it's Spider-Man, who said, extraordinary claims require extraordinary evidence. And the picture, so we need more evidence for this idea that there's something invisible out there. Unfortunately, measurements like these ones actually confirmed another measurement that we'd made earlier on. So you go to our next slide, we can see the person who made that measurement. This is Vera Rubin. She was active from the 50s to the 80s or so. She was one of very powerful, very brave woman, being able to do a PhD in the 1950s when there was massive discrimination on a formal level. When she was doing her PhD in the 1950s, she wasn't allowed to go to her supervisor's office because women weren't allowed in that part of the building. That's how awful things were in that early period. But she powered through and became a very high-profile astronomer. We're now naming things after her. That's how successful she was in the end. Now, what Vera Rubin was looking at in the 1970s was spinning galaxies. So galaxies all spin. There's a spiral galaxy like our own Milky Way. That's an artist's impression. But we know that they spin round in the direction that it looks like a whirlpool of stars all spinning round together. We see them rotating. And Vera Rubin was one of the first people to be able to measure how much galaxies were spinning, how fast galaxies were spinning by, so how fast they were rotating. And she found something extremely surprising when she made this measurement. If you go to our next slide, I've shown you the graph that she made and then a slightly easier illustration that I find helps me understand what's going on. What Vera Rubin found was that these galaxies were spinning so fast that they should be throwing themselves apart. So it's a bit like if you have a children's roundabout, like that one in the right-hand photo. If the roundabout's spinning very slowly, then the children don't have to hold on very hard at all. They can just stand there. If you spin it a bit faster, the children have to start to grip, or else because they get pushed outwards by their centrifugal force that pushes them towards the outside of the roundabout. excuse me, if you speed the roundabout up really, really, really fast, the children get thrown off, completely off the roundabout into the sandpit nearby. And Vera Rubin saw the analogy of that with our galaxies. Vera Rubin saw these galaxies that were spinning so fast, especially at the edges, that people on them, or that the stars on them, the equivalent of our children trying to hold on, would be thrown off, and the galaxy would just fly apart if the only thing that was holding them together was the gravity of the stars. So Rubin showed that these things were spinning so quickly, there must be an enormously bigger source of gravity than we can actually see. So once again, the same idea that there was something invisible holding these galaxies together. So that's two of the pieces of evidence. We found loads of pieces of evidence. Wherever we look out there in the universe, things look like there's way more invisible matter that we can't see than just the stars and the galaxies. So if you go to our next slide, that's kind of our conclusion, which is that matter that we can't see dominates our universe. That's what's the biggest amount of matter in our universe is invisible, and we call that stuff dark matter, really just because it's not as dramatic a name as it sounds. It's really just matter that gives off no light, so matter that doesn't glow in the same way that stars and gas do. So this strange dark matter stuff is our seems to be the dominant thing out there in the universe. Now, I wanted to remind you now, if you've got any questions, please put them in the chat so we can talk about them at the end. That'd be really, really exciting. And like Leo said, there's a prize for the best young person question. But there's one question that I can't answer for you, and that is the question of what is dark matter? Because despite 50 years of seeing the effects of dark matter on its surroundings by gravity, we still don't know what dark matter is. It is still to be confirmed what this dark matter stuff actually is. What is this invisible matter that seems to be pulling the universe together? That is still an open question 50 years on from the question first being asked. However, things aren't as bad as that would imply. It's not like we've made no progress in the last 50 years. We've hopefully been earning our salaries, and we've been earning our salaries by saying what dark matter isn't. So we know we've been able to rule out lots of possible things that we once thought, or that one might once think dark matter could be. So if you go to our next slide, one thing we've been able to rule out is that it's just like ordinary matter that happens not to be very bright. So lots of things out there in the universe aren't very bright. There are planets that don't glow very much. There are faint stars like brown dwarfs. But what we've been able to show in the decades since is that that's not dark matter. Unfortunately, that most obvious thing of just ordinary matter that happens to be dark doesn't work. By looking at the early universe, we can show that dark matter has no pressure. If I were to fire a stream of dark matter at you, you wouldn't even notice. It would go straight through you because it has no pressure effect. So that's a weird thing about dark matter that we've been able to prove or to demonstrate about this stuff in the decades since. Next slide is one other thing dark matter isn't. It's not antimatter. You may have heard of antimatter. It's a strange kind of material or substance that we can make in laboratories. Dark matter isn't that either, I'm afraid. There's no electrical charge. Dark matter has no electrical or magnetic interactions, which is what antimatter does have. So that's another thing ruled out, I'm afraid. One other interesting candidate is black holes on our next slide. So black holes are obviously black, very hard to see. So perhaps they could be forming the dark matter. So maybe we wouldn't be able to see them. Perhaps if there are loads of black holes floating around out there in the universe, then that could be the source of dark matter as well. That's a perfectly reasonable theory. We know there are black holes out there. We've seen black holes out there, but unfortunately, we know there aren't enough black holes to be able to explain dark matter. If there were, we'd see something called micro-lensing. So black holes would occasionally drift between us and stars, and they would do a lensing effect, just like we talked about before, and the star would get momentarily brighter and then darker again. So we've ruled that one out as well. So that's a a bit sad. We've been able to rule out all the good ideas or many of the good ideas we've had so far. There are still surviving theories, though. On our next slide, I've listed a few of them. I won't go into these, but there are theories like exotic particles, new laws of gravity, extra dimensions. All kinds of weird theories are out there for trying to study what dark matter might be. So these are all still extant theories. These are all reasonable theories that might explain dark matter. We've not been able to prove any of them yet. Particles is probably the most plausible, just because particle physicists love making particles. They do it all the time in big reactors like CERN, the famous one in Geneva. So there's loads of reasons this could be true. But we need more data, ultimately. We need to study dark matter more and look at the effects it's having more on its environment to understand exactly how it's behaving. So I've shown two examples of how we do that on this next slide. So we have experiments deep down mines, which look for dark matter directly. So the idea is if you go very, very deep down a mine, then you should block out all the other kinds of particles that exist in our atmosphere. You'll only leave behind the ones that go right through everything like the Earth. Fortunately, dark matter particles are expected to do that. So deep down in mines like this one, this is Boulby Mine in Yorkshire, potash mine, where there are a huge lab underground where they build these giant tanks of material that might just be able to detect dark matter, depending on exactly what kind of dark matter you're looking for, what dark matter is. They've got some chance of detecting these dark matter particles by looking at interactions that dark matter might have. We also haven't finished our cosmology analysis either. We're looking out there with our space telescopes, looking out into the universe, trying to analyze what dark matter might be by looking at its effect on the large-scale universe. How much does dark matter move clusters of galaxies around, and questions like that. So it's still a very much open problem, trying to understand this stuff. And it was while looking at this kind of open problem, looking at the large-scale behavior of our universe, that a group in 1998 made some even more confusing measurements. There's an old saying that if you have a problem and you build a telescope to solve it, now you've got two problems. So for our next slide, I put that little quote up. And it was in 1998 that a set of measurements of supernovae found yet a new problem for us to try and understand. So our next slide shows the Keck telescopes. So these are named after William Keck, who was one of the last oil barons to sell out his company to the giant oil corporation. So he was a billionaire in the 1970s, I think, who put a big chunk of his money into naming these telescopes or to creating these telescopes, which are at the top of Mauna Kea, the highest mountain in Hawaii. And they've been there ever since. And in 1998, they were used to make measurements of supernovae. There's a picture of a supernova on our next slide. Here it is. So our supernova is a little bright dot in the bottom left of that galaxy. So here's a galaxy in the middle, looking pretty bright, but it's being outshone by a single star which is that supernova to the bottom left. So a supernova is an exploding star. It's what happens at the end of the lifetime of a particular kind of star called a white dwarf. This particular kind of supernova outshines an entire galaxy of 100 billion stars. Is outshone by this one single exploding star. And they get bright in a day. So stars live for billions of years. They explode in one day. And that's what we're seeing there. And it gradually fades away over the course of a few weeks. And it was while looking at these supernovae that we discovered even more weird things about our universe. The Keck telescope made a survey of a very large, well, I say large number, 10 of these supernovae, or tens of these supernovae, and measured how bright they looked. So if you go to our next slide, we've got a kind of both a schematic on the right there of what a supernova looks like, and a white dwarf star. So that's Sirius B on the left. The little Sirius A is the big bright thing in the middle. Sirius B is the tiny little star in the bottom left-hand corner. So Sirius is the brightest star in the sky. If you've got a pretty good telescope, you can also see a little white dwarf star to the left of it down there. And that's an artist's impression on the right-hand side of what a supernova looks like. So these type 1b, type 1a supernovae happen when a white dwarf reaches the end of its life. And when we were looking at these supernovae back in 1998, then something extremely odd was measured about them. And that's our next slide, which is that these supernovae were fainter than we expected. They were about 10 or 20% fainter than, so less bright than we were expecting these supernovae to be. Now, this only works because we know how bright supernovae are. White dwarfs are very much the daytime television of stars. They are very, very predictable. White dwarfs are very, very boring. They do exactly the same thing every single one. They always get to the same point when they explode. They explode in a very similar way, and they always have the same brightness. So if you know how bright something is, which we do for white dwarfs because they're boring, and you can look at the supernova and see how bright it looks, then you can work out how far away it is. If I was standing right next to you up here and I shined a torch right in your eyes, you would be blinded because the torch would be very bright. The further away I got back here, if I shined the torch at you, it would look much fainter because it's further away. And you can use that to work out how far away the torch is. And we can do the same thing with supernovae. I've shown the, on the next slide, just to really illustrate how awful astronomy data is. Here are the supernovae that were measured in 1998 and how bright they were. Oh, we've lost the bottom of the screen, but what we're looking at on the x-axis there is how the expansion of the universe. So the Big Bang is at the right-hand side, the beginning of the universe, and the far left-hand side is right now. But these galaxies are all higher up than expected. They're fainter, and that meant they were further away than we expected. So what that told us, so the data is much better right now. At this time, I would have been extremely suspicious when someone came along and said, clearly the red line is a terrible fit to your data, because that's a very difficult question to answer. But we've got far much better data now, so it's much easier. It's much easier to see in the modern version of this graph. But the next slide tells us the conclusion that we come to about these supernovae, which is the universe had expanded more than we expected while the light was traveling from them to us. It takes billions of years. These things are billions of light years away, so it takes billions of years for the light to get to us. And in that time, our universe had grown much more than we thought it was going to. We always thought it would grow slowly. The universe is growing faster than we ever thought it was. And the conclusion we come to then is the next slide, which is that our universe is accelerating outwards. Some kind of bizarre anti-gravity effect out in the universe is pushing all the galaxies apart. That is as weird to me as it may sound to you, that there's some kind of bizarre anti-gravity effect going on out there. We already had one thing called dark matter, so it was quickly decided that we should call this phenomenon, not the substance necessarily, but the phenomenon, that we should call it dark energy. Dark energy is our name for this idea or this phenomenon of our universe accelerating outwards. And if dark matter was mysterious, this is even more mysterious. Our best guess, our simplest guess, is an energy field that's everywhere in the universe, but even that's extremely strange. And so my day job is trying to make measurements that will tell us how fast this effect is happening. Is it changing? Is the acceleration a constant? Is it getting less? Is it getting more? That's what we're trying to understand in the modern universe. But this energy seems to be everywhere and seems to be pushing the universe apart. And that's what we've spent the last 25 years trying to understand. So the conclusion to all of this is my next slide, which is that we think that only a tiny fraction of our universe is stuff that we can actually see and that we know we understand. So only about 5% of our universe is made of the kind of atoms that we are made of. Almost all the rest is made up of this dark matter, mysterious matter, pulling things like galaxies together, holding them together, and this even weirder dark energy, which is blasting the universe apart. So thank you very much for joining me. That's the end of my little thing now. Thanks to all the nice people on the internet who made all the lovely photographs that we put here. So thank you very, very much. Thank you very much for listening.
And thank you very much indeed, Joe. That was absolutely wonderful. And in the best spirits of Wigtown, as we would like to remember it, let me just say that I have my own way of describing dark matter and dark energy, and that is a pint of stout. If you consider the little bit of white foam at the top of a pint of stout, which we would normally be sharing in Wigtown, for those of us who do take a tipple, the rest of it is Joe's dark matter. Mm-hmm. I mean, it's mind-boggling to think that the universe that we know is just that tiny little bit of bubble at the top of a pint of stout. Joe, we've had some wonderful questions, and they vary quite a deal, which is good. We're very pleased. We like a lot of variety. So I'd like to start with Joyce, who contacted us to thank Big Bang for pointing out how many women are involved in science. And she wonders, why it is that there isn't more said about them. She's particularly interested in Vera Rubin. I should mention that we will be talking about Vera Rubin tomorrow at 5 o'clock on the Big Bang, because Vera Rubin Observatory is about to come online in Chile, as Joe mentioned. They've named one of the great telescopes on Earth after this wonderful woman. But Joyce wonders, is there more that you can find out, Joe, about Vera Rubin?
That's a great idea. Yes, I believe there is at least one biography of her. I couldn't swear to that, but I believe there is. If you look at the Rubin telescope, they've got some nice information about her as well, about the person it's named after. But no, very sadly neglected. It's only really recently that we've been starting to kind of acknowledge this contribution. Obviously, for many, many years, women were just excluded from the academy. They always found ways of getting involved in research in some way or other over the centuries. So it was, but it's absolutely true that the contribution of women to these kind of things has been hugely neglected, and it was obviously suppressed at the time as well. But no, we're now realizing that there's all these contributions going back centuries and centuries. So yeah, absolutely. And now of course these barriers are dropping away, and we're really seeing contributions that are make people being finally allowed to make the contributions they could always have made.
Yeah, no, I knew Vera Rubin, and she was a wonderful woman. And of course, we think as well of Jocelyn Bell Burnell, a good friend of mine. Jocelyn, of course, contributed to the discovery of pulsars. Two men got the Nobel Prize, yep. And there's been a lot of discussion about that. Jocelyn herself, I should say, is very magnanimous about this, but there are a lot of people very angry that she did not get recognized by the Nobel Committee. And of course, another woman, again space related, but in a strange sort of a way, who has not been up to now properly acknowledged in much the same way as Jocelyn, is of course Rosalind Franklin, the woman who helped to describe the shape of DNA, the double helix. It was Rosalind Franklin's work in crystallography, X-ray crystallography, that allowed Crick and Watson to make their great discovery, for which, of course, they got the Nobel Prize. Yeah. But I'm very glad to report, space-wise, that I'm actually in Marseille, in France, and just up the road from me this week, they've been testing the Mars rover called Rosalind Franklin. And in 2 years' time, Rosalind Franklin, the rover, will land on the surface of Mars. Fingers crossed.
I'd also like to mention Henrietta Leavitt, also a very interesting woman, Henrietta Swan Leavitt. So the thing that we now call the Hubble expansion of the universe, so Edwin Hubble, very good astronomer, that the Hubble Space Telescope is named after. He got all his data, a big half of his data, from a woman called Henrietta Swan Leavitt, who back then was they regarded them as computers, was the phrase they used. Women were doing the actual calculations, the actual analysis, and she was the member of the astronomy team who worked out how bright a special kind of star was, or she noticed a particular pattern in the kind of stars. So that directly led to Edwin Hubble discovering that our universe was expanding. So the whole concept of the expanding universe goes back to Henrietta Henrietta Swan Leavitt back in the early part of the 20th century. Also a very, very interesting woman. Yeah.
Yes, I think perhaps for next year's Big Bang, we might actually have an entire session on the subject, because as you speak, I can think of another half dozen women who've made extraordinary contributions. And to be fair, some of them were recognized in their day, but generally only because they were associated with famous men. But we won't go into this any further, because there are a lot of questions, Joe, and I'd like to get to some of them. Mike has an interesting, and this goes back now to the meat of what you were talking about. Mike challenges you and says, what other evidence do we have of dark matter apart from the rotation and stability of spiral galaxies?
So my favorite, well, so apart from the lensing, which I talked about in this lecture, my favorite example is to do with how matter grows. So when we look out into the universe, we see patterns in where galaxies are. So galaxies are everywhere, but they're not random. There are some areas of the universe with more galaxies than others. There are sort of empty regions that we call voids, and there are regions with loads and loads of galaxies called clusters, and everywhere in between. And those patterns that those galaxies form depends very strongly on gravity, because it's gravity pulling galaxies together that makes them form these big clusters and big things. And we can look at the evolution of those things with time. And the way we can do that is by looking back in time. One of the great privileges of being an astronomer is that you get to look back in time. And that's because when you look out at something very, very far away, you're also looking back in time. Because if you look at a thing 1 billion light years away, the light's taken 1 billion years to get from it to you. So you're looking at it as it was 1 billion years ago. So as we can look back in slices, or as we look back in time, we can see the evolution of how gravity is pulling things together across the universe. And that, again, very strongly implies this additional component. We can see how fast matter is clustering together. And once again, that absolutely implies you can't fit those patterns that we see without there being dark matter as well. And that goes all the way back to the beginning of our universe. We have an amazing data set from the very, very early phase of our universe, just a few 100,000 years after the Big Bang, called the microwave background, which is a sort of radio signal we can see in every different direction. And that too has this same property. It has very, very beautiful, very, very precise pattern to it. And that pattern is very, very, there's really no good way of explaining or predicting what that looks like and how gravity could have made that happen without having some dark matter in there. So it's obviously extremely difficult to prove, and there's loads of theories. And indeed, one of the theories I kind of listed as an alternative is this idea that maybe there's no dark matter, but we've just got our laws of gravity wrong. So maybe there is this, what we're calling dark matter is actually a manifestation of our misunderstanding. That's still possible. That's quite hard to make work. If you try and write down a theory where that works, it's quite difficult to do, but it's certainly not ruled out as a possibility. So this dark matter may be no more than a reflection of our own ignorance.
James has an interesting idea. I think it's a bit cheeky in scientific terms, but I quite like it. He wonders about the possibility that this acceleration could be attributable to the gravity from an infinite universe rather than to dark energy. That's
a good question. So as far as we know, obviously we can't say if our universe is infinite or not, because there's a limit to how far we can see. So it's about 14 billion years since the Big Bang, and that sets a limit on how far we can see things, at a distance. So we can never say if the universe is infinite or not. We have a kind of lower limit on its size. The problem with an infinite universe doing this is if it's infinite in both directions. So there's stuff over in that direction, and there's more stuff over in that direction. So that if that's pulling us in all directions, it turns out that effect isn't strong enough to accelerate you overall. So we can sort of add up that quantity, and that's actually one of the early things Einstein did, was to solve these equations with his new theory to say how much that was happening. So if you put together those forces from that direction and that direction, you can work out the total pull from an infinite universe, and you find out it isn't enough. It's not enough to do this effect. Unfortunately, there needs to be something else.
It does seem you raised the question yourself. What is dark matter? You raise a question which I think, let's face it, most likely will be answered by perhaps and hopefully young people who are listening to us today. This is a challenge, I think, to a new generation as well, to go out there and start stretching the bounds of possibility. We've a couple of questions from the winner of our book token, Emma, who has a couple of very interesting questions. Her first one relates directly to this, and she wants to know, how are you attempting to find out what dark matter is, and do you think there will be any breakthroughs anytime soon?
That's a good question. That's a very hard question. So there are different ways. So people like me, cosmologists like me who like looking out at the universe, we're looking at the effects of dark matter. So we're trying to say, does dark matter have a consistent effect, or does it change with time? Is dark matter related to this dark energy? Perhaps one could turn into the other, or something like that. Does dark matter decay away? So we can answer questions like that by looking outwards at the universe. So that will help us narrow down the properties of this thing and rule out more theories. In terms of actually proving something beyond any doubt, then ideally we would like a direct detection. We'd like to really see something coming off a dark matter particle directly. And that's what these mines down in Yorkshire and elsewhere are trying to do. They have enormous tanks of stuff like xenon, so very gases that you can compress down to being very dense liquids. And they look for when the very, very rare occasions when a dark matter particle actually hits an ordinary atom. And that's incredibly rare because their particles are so weakly interacting. But occasionally it should happen. It should make a little flash of light when it does. So they look for these flashes of light, essentially, in these great bizarre tanks underground. So those things are, it's entirely possible they will make a discovery. They have been trying for quite a long time now. They've been trying, I remember there were colleagues of mine when I was doing my PhD back in 2007 who were doing these measurements, and that was, it was a long time ago with as yet no detections of this stuff. And actually, just yesterday, a new result came out ruling out an apparent detection of dark matter already. It's extremely challenging, but a kind of combination of different methods is the way to go. I think that we can have a different mix of methods to help us really get a handle on things.
And I'll close the questions with another one from Emma, actually, which I think is interesting. And this again goes back to what we were talking about at the beginning, the choices that young people have to become involved. Obviously, doing astrophysics, it's a tough old station. It's not the easiest course to do in university. Emma says she's been studying advanced higher physics this year, and absolutely fair play to her. This is not trivial stuff. And she's absolutely loved the astrophysics topic. Of course, a tribute, I think we should say at this point, to teachers and to the curriculum for involving astronomy much more closely in recent years into the science curriculum. That's been, I think there's been a recognition that astronomy is a gateway into these things. But Emma asks this question. She's not going to be studying physics at college. So she wonders, is there other ways that she can continue to follow astrophysics if she's not actually doing physics in college?
Oh, that's lovely to hear. Fantastic, Emma. That's great to hear that you're interested in this. So first of all, there's depending on which program you're in at university, there's different programs that will offer you electives in some cases. So if you're lucky enough to be going somewhere where you can do a sort of side course, then you might be able to do one in astronomy there. And then they vary a great deal in what they focus on, but that's definitely worth considering as well. This is a book festival, and there's some fantastic astronomy books and astrophysics books, especially coming out in recent years. So there's books whether you want to look at the cosmology as a whole, whether you want to look at the origins of stars or the first light in the universe. There's a huge range of fantastic books that in many cases, wonderful people have written as well. So there's some great popular science looking at astrophysics in particular. And I would always say, delve down to it's often great fun to find a niche, find one area that really excites you, whether it's exploding stars or the Big Bang or any of these areas. Pick one and just and find some of the amazing science books that have been written about it.
Wonderful, wonderful. Thank you very much, Joe. So just as we wind up, Joe, I just wondered, and there's a reason I'm asking this, because we're going to go to some live television to end our session this afternoon. But the AMS, this instrument aboard the International Space Station, the Alpha Magnetic Spectrometer, to use its technical name, this is an instrument which a lot of particle physicists hope will produce a Nobel Prize. This may be the first Nobel Prize literally coming from an instrument in outer space. Does that instrument aboard the International Space Station, which of course passes over Britain and Ireland very regularly, is that in any way going to help with this search that you're involved in?
Very indirectly, but ultimately, yes. That kind of detector looks for particles coming from outer space, things like cosmic rays. It looks for sort of things along those lines. So particles that have either been accelerated by the magnetic fields of our galaxy or have otherwise come from highly energetic phenomena. And they're not going to directly detect dark matter with that kind of thing, but it helps us understand the background. It helps us understand what kinds of particles are out there and get a handle on those. And it helps us understand what supernovae look like, because they give off these particles as well, and what our galaxy is shaped like magnetically. So not directly, but it's as part of building up a bigger picture, a bigger understanding of the structure of our galaxy. And it's a wonderful tool for things like that.
Dr. Joe Zuntz, thank you very, very much indeed. It's been an absolutely wonderful talk, a wonderful interaction. We all just wish we were together in Wigtown, but warmest congratulations on a wonderful talk. And we're going to go now live into outer space. This is the two astronauts. We're watching live pictures from the International Space Station. The astronauts are Kate Rubins and Soichi Noguchi of the Japanese Space Agency, so an American and a Japanese astronaut. They're right on the end of the big, long pylon that holds the solar panels for powering the International Space Station. Some of the pictures coming back today have been absolutely astonishing, because they're right there out on the edge of the space station, and it's been a joy to watch. It's very, very important work, because the space station cannot continue unless they add extra power panels to the station. What we're seeing now live is actually what Kate Rubins is seeing in through her camera on her head. We're actually seeing live pictures from Kate Rubins' camera on her helmet. And you can see that she's packing up. In fact, they're nearing the end of this spacewalk. They've been out for the last 5 hours. It's just a demonstration of how much is going on in space, both human spaceflight, which is, of course, a joint endeavor of all the countries on Earth, really. The Chinese aren't involved in the International Space Station, but they're building their own and planning to launch it this year. We have, of course, the American rover that just landed on Mars. The Chinese rover will land in May on Mars. So very, very exciting times. Exciting times, as we've just heard from Joe Zuntz, also in astronomy. And we're hoping, as always, to reflect this in our discussions during the Big Bang. So I'll be back at 5 o'clock tomorrow evening with a wonderful presentation. We're going to be talking about astrophotography, and we're going to introduce you to a truly fascinating and wonderful young woman from a Wigtown woman herself. So don't miss that at 5 o'clock tomorrow evening. Until then, goodbye.